Hi everyone. Today we're going to start building this idea and putting together average rate of change and instantaneous rate of change. Okay, and how they compare to one another, how they're different, what it looks like on a function. So, to get ready for our lesson today, we first want to look at these four pictures and we want to identify what here is a secant and what is a tangent. So you might want to pause your video and do a little Googling and to find out, well, what is a secant line and what are the characteristics of a tangent line. So a secant line is going to go through 2 points on your graph. Okay, so that means that graph A and graph C are both secant lines. Okay, a tangent line is going to go through 1 point on the graph. So B is a tangent, and D over here, the line that in question is actually the red one. So you can see that that's just going through point P there. So that one is tangent as well. Okay, now I would like you to pause and in your notes write down, the difference between average and instantaneous. Okay, so you've had a chance to write that down. So really what we're looking for here, average, you may have had something like over a period of time. Okay, when you find the average, you need at least 2 points. So that's something that we could add as well. And then instant. Okay, instant would be at one specific point. All right, so maybe you had something similar written down to each of those. All right, so to start here, we're first going to talk about very, very simple concept of slope. Okay, so we know what the formula for slope is. It's y2 minus y1 over x2 minus x1. So, we're being given this diagram here. They're also telling us what our ordered pairs are. So we know when we first learned how to do slope, we were told to label those points. So 7 minus 3 over 5 minus 2. Okay, so we have 4 over 3 as our slope. Okay, so now I want to stick with the same idea of slope, but I kind of want to change our thinking of the notation that we're using for each of those ordered pairs. So if we say that our first ordered pair is A and our second ordered pair is B for each x value, well then that means that in order to get that y value, we had to have done f of A, meaning we took our x and we plugged it into the function. So I'm really just using function notation here as a different way of writing our ordered pairs rather than x1, y1, x2, y2. So that new formula now for my slope would become something like f of B minus f of A over B minus A. So it's still representing, the change in y over the change in x, but we're kind of just starting to make our notation a little bit more mature, okay, because we're trying to get to a certain point here. Okay, so by the end of the video, all of this is going to come full circle. So what we have now is a formal definition and formula for average rate of change. So average rate of change is f of B minus f of A over B minus A. Okay, so that's looking at the average over a period of time. You can see it in the diagram here. So take a second and quickly write down, what does this line here demonstrating the average rate of change, what does that represent? Is that a tangent line or is that a secant line? So the average rate of change is a secant line because it goes through 2 points. It's going from A to B. It's over a period of time here. Okay, and we said in our little warm-up example there, when we wrote out in our own words, what does average mean to you? Well, average, we said, should have been over a period of time. It involves 2 points. Okay, so average rate of change is the same thing as the slope of the secant line. All right, those are the same things, and this is our formal definition here. Okay, so remember, it's always the change in a value of a quantity divided by the elapsed time. Okay, so if we're given, remember this right here is an interval. Okay, so if we're given an interval over which we want to find the average rate of change, f of b minus f of a over b minus a. So this is, let me maybe change my color here. So this is your a value and this is your b, but you do not have the f of b or f of a. So before you can start the problem, you actually need to evaluate. So f of b is finding f of 3. So we would take that and plug it into our function. And then we would do the same for f of a. So f of a is 1. So now that we have those values, we can plug them in here. So we know that this is a slope. I'm going to call it m just for the time being. And we're going to find our change in y over our change in x. Okay, so this is the average rate of change. This is also the slope of the secant line. Okay, so now let's think about this in a real life situation and kind of determine the pros and cons to average rate of change and what it's really telling us about a situation. So if a car is traveling 120 miles in 2 hours and 30 minutes, what is the average velocity? So average velocity is the same thing as average rate of change. Okay, over the entire 2.5 hour time interval. So remember that average rate of change is the change in some quantity over the time that has elapsed. So we have our 2.5 hours on the bottom, and the change in our quantity is that we've gone from 0 miles and then we've traveled 120 miles. Okay, so we can say that our average velocity or our average rate of change here is 48 miles per hour. But what does that really tell us about the situation? And is that really giving us a whole lot of detail? So if you notice, the average rate of change doesn't tell you how fast the car is traveling at any given moment. It tells you over the entire time period. So the car could have gone a constant 48 miles per hour the entire way, Or you could have sped up during certain intervals. It could have been slowed down. You could have even been stopped for a period of time over that 2.5 hours. So there really is something to be said about the length of the interval that's being used to calculate the average rate of change. So we really want to inspect the size of the interval, the length of the interval, how much time is elapsing, and see, well, what happens when I elongate or I shorten that period of time over which I'm looking for my average rate of change. So we're going to do a little bit of an experiment. Okay, so we're going to calculate these 5 individual rates of change for this one function. Okay, so we're using the same function every time, but we're looking at 5 different time intervals. So from x equals 3 to x equals 5, we're looking at a time interval of 2. From x equals 3 to x equals 4, we're looking at a time interval of 1. And then you can see we're progressively getting smaller and smaller for our time intervals. So we really want to see, what happens as I shorten or I lengthen these time periods. Okay, so in order to solve this, I'm going to do a little bit of the arithmetic beforehand, so then I can just set up each average rate of change without having to do calculations in between each one. So what I mean is, for each of these individual 5 problems, I need to evaluate each x value. So I'm looking to evaluate f of 3, f of 4, and so on. Okay, so I'm taking each one of those and I'm plugging it into my function. Okay, and so on. So for time and space here, I'm not going to set each one up, okay, but we're going to go ahead and evaluate. So we're just plugging this into the calculator. F of 3 equals 6. F of 4 equals 13. All right, and so on. All right, so you want to make sure that you write all of those down. Those are the values I'm going to be using as I evaluate each average rate of change. Okay, and so I'm going to number each one of these problems because I am going to have to use a second slide for space here, okay, as I go to evaluate. Whoops, I can't even number correctly. Okay. All right, so our first average rate of change. So we're doing f of b minus f of a over b minus a for our first problem, x equals 3 and x equals 5. Okay, and we get an average rate of change of 8. All right, so we're just setting each one of these up. Okay, and you can already notice perhaps a pattern here as you're solving each one of these. Okay, so I want you to make an observation right now and make a connection, if you can, between the length of the time interval and the average rate of change, and what the average rate of change, the meaning for it actually is. So pause your video, see if you can write down some sort of statement about the connection between the time interval and the average rate of change. All right, so let's see what you came up with. So the smaller the time interval, the more closely the average rate of change, okay, is going to approximate, or it's going to represent the instantaneous velocity. Okay, so the average rate of change is over 2 points over a period of time, and the instantaneous is 1 point. So if you think about the average, as those 2 points get closer and closer together, they're turning into perhaps 1 point, or the space between them, the period of time between them is becoming smaller and smaller and almost negligible, that the average rate of change is now starting to represent the instantaneous, because the instantaneous is at 1 point. So as the distance between 2 points becomes smaller and smaller, they're merging into becoming the same point. So we identify the space between the 2 points, the time period, as h. So if you have a starting point of x and then a second point of x plus h, h is that distance, that time interval in between the 2 points. So as that value of h approaches 0, okay, you're getting closer and closer to representing an instantaneous velocity, which happens at one specific point. Okay, so the distance between those two values is so small that it's essentially 0. Now, the way that we write an expression when it approaches, so approaching a value, this is the key word there. Okay, this was one of the very first units that we did. What kind of expression do we write when we are approaching a value? Think about that for a second. Okay, so I'm just going to draw a diagram kind of talking about the situation. Okay, so if this is my point, x, and this is my x plus h, so that means that the distance in between these, just make this a little nicer, the distance in between these is represented by h. Okay, so as these 2 points get closer and closer together, so maybe this one's moving down, okay, the h is getting smaller and smaller, and it's starting to approach 0. Okay, so what we're trying to formulate here and finally come full circle and put together is an equation for the slope of a secant line and the slope of a tangent line and what they represent. Okay, so we've already said that the secant line is the average rate of change. And we had that, kind of more mature and formal formula. We had f of b minus f of a over b minus a. You could also see f of x plus h, because this would be, this would represent like our b point, and this would represent our a point, minus f of x over x plus h minus x. Okay, so in the denominator here, when you simplify that, x plus h minus x is just h. Okay, so that really And we like to use this x and x plus h notation because that's what we're going to use in just a second for the tangent. And we like for our notation to be cohesive between the two things. Okay, so I asked you, a minute ago to kind of think about, well, what kind of expression do we write when we approach a value? So we actually use a limit. Okay, if you remember that. So the tangent line here, this is going to be the instantaneous. Instantaneous rate of change, because this is at 1 point, 1 instant. So we actually use a limit. So the equation is going to be very, very similar, practically identical to the average rate of change, except for the fact that it is a limit. So we said that as these 2 points get closer and closer together, the h is approaching 0. So we actually want to evaluate that expression when h equals 0. So in order to find the slope of the tangent line, we do the limit as h approaches 0, and we actually use the same expression from the average. All right, so the average rate of change, you are just finding slope. You can think of it as f of b minus f of a. Okay, that's definitely true. The slope of the tangent line, the instantaneous rate of change, we use this limit formula. Okay, so I have a couple, I've got one more example. I actually want to put this into practice. So we're just going to look at practicing the average rate of change problems. And in the next lesson, we will practice the instantaneous using that limit. So problems that you'll see today is just, finding the average rate of change. So they're giving you the function, and now, they're giving us 2 points. So we know the first point is x equals 2, but then the second point, we don't necessarily know where it's going to be. We just know that it is some distance away, h. Okay, so we know that we're finding the slope. This is secant. So f of x plus h minus f of x. Okay, and we know that it's really x plus h minus x. Okay, and that in the denominator there, we're really just going to have h. Okay, so the first thing that I need to do is evaluate, just like I did a couple examples ago, I have to evaluate f of x plus h, and I have to see, well, what is f of x? So f of x plus h is going to be x plus 2. So anywhere in my function that I have an x, I'm going to replace it with an x plus 2. Okay, so that means I'm going to have to FOIL. Okay, so that is f of x plus 2. F of x is always given to you, so you don't actually have to do anything for that. That's just your function. Okay, so we're going to set this all up. So we're finding the slope. That's what the average rate of change is, so we use m. So f of x plus h, that was 2x squared plus 8x plus 13. Okay, and we are subtracting from it our f of x, which is 2x plus 5. But you want to make sure that you use parentheses. Okay, so now x plus 2 minus 2. No, I'm sorry, not x plus 2. 2 plus h. Okay. So that is your x plus h minus x. So 2 plus h minus 2 in the denominator. Okay, we can do some canceling. Those are going to go. Okay, and we're going to be left with 8x plus 8 over h. So we are going to have an h in our final answer. Okay, we're going to leave it. Whoops. Didn't mean to draw right through that. We're going to leave it. Okay, and so that is going to be